Today, we're going to look at the CSAW 19 CTF challenge Beleaf, and we're going to solve it by learning Ghidra and learning some Ghidra scripting. For a beginner reverse engineering challenge, this one was actually a lot of fun and I really enjoyed it, and I hope you do too. So let's jump in. Starting in the Module 3 directory, let's see what's inside this folder. Okay, so here we have a readme.md. That's going to be the solution file. It's going to tell us how to solve this problem. So we're not going to look at that. The other file that we have is the Beleaf file. This file should be the actual challenge. Let's go ahead and run the file command on it. And we can see here that it is a ELF executable. That basically just means that it's a program that we can run. If you're not familiar with what an ELF file format is or what it's used for, ELF is an acronym for Executable and Linkable Format. All programs in Linux and other Unix systems use this file format for their programs. They're similar to PE file format on Windows and the Mako file format in Apple OS X. This means that if you see a file that is an ELF executable, you can likely run it as long as it's compiled for your system. So let's go ahead and do just that. We'll run the Beleaf challenge program and see what happens. What we get is a prompt that says enter the flag. Let's see what happens when I type something random in. Okay, so we just got the string incorrect. It would have been pretty wild if I had guessed the flag on the first try. Since we're trying to find a flag that is a human readable string, it makes sense to see if we can quickly identify a flag in the program by running the strings command on the application. If you're not familiar with the strings command, it's a simple command that will search through a binary file and identify a series of values in the binary that fall within the ASCII range of hex 20 to hex 7F and end in a null byte. By default, if the strings command finds a series of bytes in the ASCII range longer than 4 bytes and ends with a null byte, it will consider this a human readable string and print it out to the console. As we can see, there can be false positives. For example, this string g@:lo+6 is probably garbage. In addition to false positives, the output is going to contain strings that you are likely to find in any executable you run the strings command on. As an example, the strings.txt and .data are standard names for segments that hold the executable's code and data respectively. More interesting are the strings that we saw when we actually ran the Beleaf program. Enter the flag, the prompt, and the words incorrect and correct. As we don't see an obvious flag in this output, these strings will give us a starting spot in the binary to begin our reverse engineering. We will start by finding cross-references to these strings and using those cross-references to identify what causes the word correct to be printed. If you find yourself wondering how I know none of these strings are the flag, it's because a CTF flag usually follows some sort of standard format, often having the name of the CTF as the beginning of the flag or the word flag itself as the beginning of the flag, followed by some unique data between an opening and closing curly brace. So let's go ahead and open up the application in Ghidra and start digging through it. I already have a Nightmare CTF project with all the binaries imported. You can import all of the binaries using the batch import option. Just go up to File, Batch Import, and then select the folder that you want to import. I selected Modules. Normally, you would now click the Select Files button, but I'm not going to do that as I've already imported everything. Let's go ahead and double click on the Beleaf binary and bring up the code browser tool. Let's click Yes, followed by Analyze on the next dialog to analyze the binary, keeping all the settings default. The analysis shouldn't take very long as this binary is really small. The next thing we need to do is to find the logic that processes our input so we can figure out what the flag is. There are two ways we can start. The first way is to find the main function and start from the beginning of the program. The second and probably better way is to find the strings incorrect and correct in the binary and look for where they're used. They're almost certainly being used in conjunction with a function call such as printf. And they're probably near the decision logic that determines if we typed in the correct flag or not. One thing to notice is that the binary has had its symbol stripped. This means that none of the functions or variables will have human readable names, and Ghidra will assign them one based on their address. This makes identifying main a little bit harder, so we'll just start by looking at our strings instead. This tab should look similar to what we saw in the output of the strings command. However, you might notice it's a little bit different. That's because Ghidra will look for strings in the same way as the strings command, but it will also apply some heuristics to remove anything that's obviously not a string.
As you can see, this isn't a perfect process and there are still false positives.
If we click on one of our interesting strings in the strings view, Ghidra will take us to where that string lives in the binary. From there, we can scroll to the right and we can see the cross references this string has, which indicate where the string is used. As you can see, incorrect has 2 places where it's used, and correct has 1 place where it's used. This makes sense as there's likely multiple ways to be wrong when we type in a flag, but only one way to be right. Another thing to notice is if a string is smaller than around 4 characters, such as these %s bytes, Ghidra might not pick it up as a string. Small format strings are really common examples of these. This is easily fixed. Simply right-click on the first character, go to Data, and then select Terminated C-string. This will mark these bytes as a string and will have the added effect of making your decompilation look better. Since our goal is to get the word correct to be printed out, let's see where in the program this correct string is actually used by double-clicking on its only cross-reference. Then we'll switch over to the Decompilation tab and start looking at the code. This function quickly stands out as being the main logic of the program. We'll go ahead and call this function main. It might not technically be the main function, but it'll work for our purposes. We see the prompt enter the flag being printed to the screen, a call to scanf, which reads a string as well as our incorrect and correct strings being printed. There's a bit going on here, so let's start from the top of the function. To start, we have a call to printf, which prints out the enter the flag prompt. It's always a good practice to rename your functions and variables to something more human readable when you can. It really cleans up the decompilation and makes it easier to follow. Since we know that local 98 will be the buffer that contains the input we type in from the keyboard, we'll go ahead and rename this to input buffer. One thing to note here is that scanf doesn't have a limit on the number of bytes it will read in, and our input buffer has a maximum size of 136 bytes. This means that it would be possible to overrun the buffer and cause a buffer overflow, a technique we will see in later problems. You don't have to have noticed that to solve this problem, but it's still good to point out so that you start to quickly spot similar issues for future problems. The next thing we do is get the length of the string by calling strlen. So let's rename the variable that it saves the length to, and we'll call it input bufferlen. What we can see by the following if statement is that if our length stored in input bufferlen is less than hex 21 bytes or 33 bytes in decimal, then we will fail, print incorrect, and exit immediately. Sometimes it's helpful to have comments, so I'll add one now by pressing the semicolon button on the keyboard. When recording this, I made the mistake of typing more than 33 bytes long when it should say at least 33 bytes long. Let's shift our attention to the for loop and start with the first variable, local B0. If we middle click on local B0, Ghidra will highlight all of the places where this variable is used. As we can see, it's used as an index into our input buffer, so we'll go ahead and rename this variable to index. What we are left with is an easily readable for loop where the index starts at 0 and goes up to the length of the buffer and is increased by 1 each loop. While recording, it's at this point where I made my first major mistake. I misinterpreted this cast shown on the screen. I originally thought that it was casting our input buffer to an array of integers in order to pass data into the function 4 bytes at a time. This is not what it's doing. Instead, this cast is first getting a single character from our input buffer, then casting that single byte up to a 4-byte integer and passing it into the function. This causes a bit of confusion as I try to understand the function and quickly realize it doesn't make much sense. This issue is then resolved using dynamic analysis in GDB to show that the parameter passed to the function is just a single character. We'll fast forward through that part as it's not very instructive. That's much better. Now that that's fixed, we can go ahead and analyze this function properly. So far, we've renamed a few variables, such as our first parameter has become buffer part, a local variable which is named index, and I have given a name to a really strange table containing some ASCII values, the name strange ASCII table. Let's take a look at the conditions of this while statement. It starts off by ensuring that the index variable is not equal to -1. That would be a terminating condition and the loop would exit. Then it ensures that buffer part is not equal to the value at strange ASCII table plus our index times 4. This may look a little confusing, but anytime you see a table, an index, and a multiply by 4 or 8, it's almost certain that the math is skipping through a table 4 or 8 bytes at a time, usually in order to read integers or pointers. What this means is we will execute the body of the while loop as long as our index variable does not become -1 and the value we read from the strange ASCII table is not the same as the value passed into the function. If any of those conditions are true, we return the calculated index and exit this function. There are two main if conditions, and though they look a bit long and scary, they're actually pretty simple. The first if statement checks if the value retrieved from the strange ASCII table is bigger than the value we passed into our function. The second if statement checks if the value retrieved from the strange ASCII table is smaller than the value we passed into the function. Depending on which is true, we will either multiply the index by 2 and add 1, or add 1 and multiply by 2. And repeat this loop until index either overflows to -1 or our input value matches the strange ASCII table value, at which time the function will return the final index number to the calling function. Let's go back up to the calling function and see what this index value is used for. Okay, here we are, and lvar1 is the index returned from our function. Let's go ahead and rename some variables to help with the readability of the decompilation. Since we've already used the name index, let's differentiate this variable by calling it return index. Then we'll change the name of the index calculating function to calculate index. Clever names, I know. The next thing that catches my eye is that our return index is being compared against the now familiar pattern of a memory address plus our for loop index times 8, which is likely an 8-byte quad word lookup in a table. If our return index doesn't match what's expected in this table, then we get the message incorrect and fail the challenge problem. Conversely, to get the correct message, all return index values must match what's in the table in order. Let's take a closer look at this table before we move on. If we hit B on the keyboard, we can cycle through various integer data types. Press it 4 times and you will change the data to a quad word. If we do this for enough values, we can clearly see that our suspicion was correct and that this is a table of quad words. That sounds obvious, but what's more important is that this is a list of expected indexes as quad words in the order in which they're expected to appear in our solution. Let's go back and rename this table to something like valid indexes array. In addition, since the word index has become a bit overloaded, let's change index variable's name to counter to help differentiate them. Let's take a moment to understand what's happening graphically. In the function calculate index, the algorithm can be imagined as a binary tree like the one on the screen. The nodes of the tree are the values in the strange ASCII table. The nodes locations are given by either the formula index times 2 plus 1 or index plus 1 times 2. Whether our input value is bigger than or less than the node value determines which formula we apply. If our input value is less than the value in the ASCII table, we go to the left. Conversely, if our value is bigger than the ASCII value in the table, we go to the right. Every time we go to the left, we apply the formula index times 2 plus 1, and every time we go to the right, we apply the formula index plus 1 times 2. If our input value is the same as the ASCII table value, we don't apply any formula, we just return the index. Finally, if the value isn't found in strange ASCII table, the index value will overflow to -1 and the loop will exit. These index values are then checked against the valid indexes array one at a time, and as long as they're in order, we will get the message correct. Reversing the process to convert our index values back to ASCII values is more simple than it may appear at first. All we do is take each value in the valid indexes array and find the ASCII letter in the strange ASCII table at that index. For example, as you can see on the screen, if we take the first value in the valid indexes array, the index 1, then we go to the strange ASCII table at index 1, the first letter in our solution is the letter F. This makes sense as the solution likely starts with the word flag. If we go to the next expected index, the index 9, we will see that it corresponds with the letter L. Because of the math involved, the array's strange ASCII table could get quite big, so pulling out the values by hand would be tedious. Therefore, I decided to write a Ghidra Python script to do it for me. This script will iterate through a list of indexes and look up the memory value at that index, writing it to the screen. The first step in writing that script is to pull out the valid indexes array. This isn't necessary as we could have just provided the script to the start location of that table in the same way that we will for the strange ASCII table later on, but this is the way I chose to do it. I wasn't able to figure out a good way of exporting this array out of Ghidra into some format that was usable in Python, so I did it manually. If you know of a good way to do it, please leave it in the comments. Since this part was a bit boring, we'll fast forward through it. Effectively, all I'm doing is taking the bytes out of Ghidra and converting it to a Python list. Now we're ready to create our script. There are many ways to create a script in Ghidra. The fastest is probably to go up to the main toolbar and click on the green and white arrow icon to bring up the script manager. From there, click the scroll icon at the top called Create New Script and select Python in the next dialog. We'll give it the name Beleaf.py so it's easy to remember. If this is the first time creating a custom script, Ghidra will make a new folder in your home directory called Ghidra Scripts. If you want, you can edit the script from there using your favorite IDE. However, I chose to use the built-in script editor since the script will be small. First, we'll create a helper function called getAddress. This helper function will convert an integer to a Ghidra address object that the rest of the API is expecting. I stole this specific function from a good friend of mine, Cetfor. He has an amazing post on GitHub on how to write Ghidra scripts. I'll link to it in the description below. Now we'll use our new getAddress function to get the address of our strange ASCII table as a new object called valuesOffset. Now we'll go grab and paste in our list of indexes that we pulled out of the program earlier. We'll add a little bit of formatting to make it look nice. Now all we have to do is loop over our index list and pull out the values from the strange ASCII table at those indexes. We need to remember to multiply our index by 4 since the strange ASCII table is actually a series of 4-byte dwords. We'll use getDataAt on the program listing, passing in our address to pull the data out of the program. I know it looks strange to call getValue twice, but let me explain. GetDataAt will return an object of type DataDB. Calling getValue on a DataDB object will return a scalar object. To get an integer we can pass into a Python char function, we need to call getValue one more time on the scalar object, which will give us an integer we can use. And now if we run our script, we get our flag printed out in the console. And there we have the flag. We believe in your RE future. If you want a copy of this script, I'll link it to a GitHub gist in the description below. One last thing, let's go back to the Beleaf directory and test out our solution. We have our prompt, and we'll type in our flag that we've now discovered. And success! I hope you enjoyed today's breakdown of CSAW 19's CTF challenge Beleaf. In the next couple videos, we're going to be moving away from strings hidden in a binary and into something more substantial, buffer overflows. If you liked today's video, please like, subscribe, and hit the notification bell. It keeps you from missing out on future videos. Don't forget to clean your bits, and we'll see you next time.